Hi everyone, Tina here, and today I'd like to talk about differentiation from first principles. You'll usually come across this idea during year 1 of your A-level course. I have made other videos on differentiation, so I'd recommend you watch those ones as well. Let's start by looking at the differentiation from first principles formula and thinking about why it works. No matter which exam board you're studying with, you're going to be given this formula in your formula book. Here's the version from the edX formula book. On its own, it can look a little bit intimidating, but let me draw a picture to explain what's going on. So there are some axes, and I'm just going to draw a curve here. So x-axis, y-axis, and let's say this is the function y equals f of x. Now, if we think about 2 points on that curve, let's call this point A and this point B. At A, we can say that this x-coordinate is called x, and therefore the corresponding y-coordinate would be f of x. And for B, we're going to call this x-coordinate x plus h, where h is the distance between the two x values. And therefore, the corresponding y value would be f of x plus h. Now, if we join those 2 points together, we get a line. And if we wanted to find the gradient of that line, we would normally do change in y over change in x. So that's just GCSE knowledge at this point. The change in y is going to be f of x plus h minus f of x. And the change in x is going to be x plus h minus x. Simplifying this gives us this. And as you can see, this expression is the same as the expression in the first principles formula. We also know from previous knowledge that the gradient is the same as the derivative, f dash of x. So the only thing left to explore is what this part means, lim h arrow 0. You read this as the limit as h tends to 0. Now, we said h was the distance between those two x coordinates. So let's think about what would happen if we shortened that distance. So if we made the h distance smaller, for example, by moving B a bit closer to A. The gradient between those 2 points would look more like that then. If we moved B again to be closer to A, the gradient would look more like that. And if you keep moving B closer to A, the gradient of AB is going to get closer and closer to the gradient of the tangent or the curve at A. So what we can say is, as h tends to 0 or gets smaller, the gradient of AB gets closer and closer to the gradient of the curve at A. If h was so small that it was effectively 0, then the gradient of that tangent would exactly match the gradient of the curve at A. So the differentiation from first principles formula allows us to arrive at the derivative via a different method to what we're used to. Example 1. Prove from first principles that the derivative of 5x squared is 10x. So if you see those words, first principles, I'd recommend you go to your formula book straight away and make a note of the formula. Then I like to define what f of x is. So in this case, the function that they want us to differentiate is 5x squared. Underneath that, I usually write f of x plus h, and that's just replacing the x with x plus h. I then copy the formula out, replacing the relevant parts. So f of x plus h is now 5 brackets x plus h squared minus f of x, which is 5x squared, all over h. We're now going to expand and simplify this, so I'd recommend you do any of that expanding algebra off to the side so that you don't have to keep writing the formula out each time. So for this one, x plus h squared, we can do that off to the side. That would give us x squared plus 2hx plus h squared when we expand. We can then take that and sub it back in. So we've got limit as h tends to 0 of 5 times that expression, so 5x squared plus 10hx plus 5h squared minus 5x squared all over h. We can then look at simplifying this. So the 5x squared will cancel, and then we can cancel some of these h's as well. So we're going to be left with the limit as h tends to 0 of just 10x plus 5h. Now, to finish it off, you just need to consider what would happen as h tends towards 0. So as h gets infinitely small, effectively becoming 0, what would happen to this expression? The 5h would disappear. So you'd just be left with 10x for your answer as required. Example 2. Prove from first principles that the derivative of 2x cubed is 6x squared. Again, it's first principles, so we're going to grab the formula, make a note. We're going to make a note of what f of x is in this case. 2x cubed. What's f of x plus h? That will be 2x plus h cubed. We're going to substitute into the formula, so f dash x is limit as h tends to 0 of that. We're then going to do our expanding and simplifying off to the side. So this time we're interested in x plus h cubed. You can do this with a binomial expansion if you want, or you can just expand triple brackets. I'm going to do triple brackets here. So leaving the first bracket as it is, expanding the second set of brackets, get this. Expand the third bracket and you get this. Simplifying, we get this. We can now take this entire expression and substitute it in here. So it's limit as h tends to 0 of 2 times that entire yellow expression. So 2x cubed plus 6hx squared plus 6h squared x plus 2h cubed minus 2x cubed all over h. Seeing what cancels, so the 2x cubed cancels, some h's will cancel as well. Altogether, you get the limit as h tends to 0 of 6x squared plus 6hx plus 2h squared. And again, to finish it off, we just need to think about what would happen as h became close to 0. This would disappear, as would this. Means you're just left with 6x squared for your answer as required. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already. And do share this with anyone else who you think might find it helpful. Thanks and see you next time.